So thank you, Michaela, for the invitation, and thank you, Michaela and Jamie, for the organization. Thank you, Margaret Morrison, for many conversations about models and football and whiskey. And apologies to Paolo, who received my slides last night, way too late for...
that line is the first source of inspiration for physicists.
Very good. So, okay, so what I want to talk about, as you see, is searches for new physics at the LHC from the point of view of theory. And I would like to talk about the change in the attitude or approach to new physics searches away from very specific models towards more model-independent searches using what people call simplified models. So I'll talk about that. It's mostly a physics talk that's supposed to tell you what we do. And then I have some questions that may be interesting for philosophers as well. It's okay. The laptop has seen many things. Laptop. Yes, that's okay. No worry, it will do. Tissue. Okay.
Tissue outside.
No, laptop is fine. Don't worry. So before we talk about new physics, I thought it's good to remind ourselves why we expect new physics. Oh, wonderful.
So it's still working.
Thank you. Thank you.
Okay. Sometimes the keyboard goes crazy in the water. It's actually quite dangerous thing to happen. There you go.
Good. All right. Thank you. So, before we move to new physics, let us briefly talk about the standard model and the way it's constructed and how we like to construct theories and what we would like to do in constructing theories and models. So the standard model is really determined by symmetries. As most of you know, there is space-time symmetry, that is the global Poincare symmetry, and then there is the internal SUN gauge symmetry, SU3 cross SU2 cross U1. And the symmetries really determine the structure of the theory. You start with the particle content, which is experimental information, and then you impose these symmetries, and the structure of the standard model really follows, essentially, as you can see it here in this very condensed form. You have gauge sector, so the fermions with their interactions with the gauge bosons, kinetic terms for the gauge bosons. You have the sector that determines electroweak symmetry breaking with the scalar potential and the Higgs field. And then you have the terms that describe the interaction of fermions with the Higgs field, and that are the terms that then provide mass to the particles. And then there is the neutrino mass sector, which is a completely different thing. And I wanted to stress this because we like to build theories that are based on very few principles. So here it's just the Poincare symmetry and the gauge symmetry that determines the structure of this Lagrangian. And it's been a very successful model or theory. But it has a few deficiencies which I'll mention in a second. Before I move on, let me just also mention briefly that we require renormalizability. That is, all the ultraviolet sensitivity that appear in quantum fluctuations should be absorbed in the finite number of physical parameters of the model. That you could relax, actually, and you could move to effective field theories and add higher dimensional operators. That's also fine. And we ignore the strong CP problem. We could actually add another term here with FF dual for the gluon field, which is perfectly fine. It's consistent with all the symmetry. So from our principle, typically we would say this term has to be there. But we know the coefficient of this term is really small because it induces things like electric dipole moments. So we know the coefficients must be small, but we don't know really why. There is a nice explanation of why this coefficient could be small by Petche and Quinn, who argued that the coefficient of this term, which I haven't written down, is a dynamical field. You impose an additional symmetry, and then this field gets a vacuum expectation value, and it naturally explains why this term is absent. And as a consequence of this broken additional symmetry, you get a particle which is called the axion. So it's a well-motivated new physics particle, which hasn't been discussed a lot for, I think, essentially sociological reasons, because you can't really detect that at the LHC. You need completely different type of experiments. But it actually has an impact on model building at the LHC in an indirect way, as I'll explain maybe later, if it comes to dark matter and model building for dark matter, the axion is a potential dark matter candidate. And if you have a theory or a model that's supposed to explain dark matter and you don't quite reach the right level of dark matter, you can always say, oh, we have axions as well, and they fill up the rest. So axions now come to the rescue if your model doesn't really describe dark matter well. Okay, so what are the deficiencies of this very successful model? There's this problem of mass. Is really the standard model Higgs field the origin of particle masses, and if you look at it, it's a really very ad hoc and unsatisfactory explanation of mass. It is a breaking of a symmetry that is not dynamical, it's just added to the Lagrangian by hand, and in all the cases that we know in nature of spontaneous symmetry breaking, it's all done through a dynamical mechanism and not just through adding a certain piece of the Lagrangian. So it's unsatisfactory, and the question is there any more to dynamical spontaneous symmetry breaking than the standard model Higgs field? And in fact, Krämer has written a paper on the ad hocness of the standard model Higgs from a philosophical point of view, if you're interested. And then there's the question, what stabilizes the Higgs mass? So if you, as you know, if you calculate quantum corrections to the Higgs mass, they are sensitive to the ultraviolet cutoff scale of your theory. And we think there should be some principle, some symmetry maybe, or something else that explains why the Higgs mass is 126 or 125 GeV and not somewhere up at the Planck scale. And then last but not least, why are the fermion masses the way they are? So in the standard model, fermion masses are simply given by this parameter here or these parameters here. These are just arbitrary couplings, and they take very different values experimentally. The top quark mass is about 300,000 times larger than the electron mass, and there is no explanation for that. And so you could think that a theory of mass somehow should explain the hierarchy of masses that we observe experimentally, and the standard model Higgs mechanism can't really do that. And then there are other things. Is there a unified theory that kind of unifies all the different interaction? Why do we have 3 copies of families? What is the origin of the p-violation? And then are these problems that are related to astroparticle physics and cosmology. What is the origin of the matter-antimatter symmetry? So p-violation, the standard model, is not sufficient, so you need some additional sources of the p-violation if you want to explain that. And then finally, what is the nature of dark matter and dark energy? And so really we still, I think, we have this dream of a final theory that should explain it all. So this is what we were after for many, many years. And the most promising candidates, I think, have been, and maybe still are, I'm not so sure about that, supersymmetry and string theory. Supersymmetry as essentially a weak scale realization, and maybe then string theory at some very high scale, unifying quantum physics and gravity. So now moving to the LHC, why do we expect any of these questions to be answered at the LHC? I think there are mainly 2 arguments in favor for new physics at the LHC. The first one is this naturalness problem. Why is the Higgs mass light, and why is it not at the Planck scale? If you calculate these kind of graphs here, so correction to the Higgs mass, you see that this correction depends on the ultraviolet scale, cutoff scale, the highest scale at which your theory is still valid, square. And so you get very large corrections, and some of you have to cancel those against the bare mass parameter in the Lagrangian to a very, very high degree to get a sensible light Higgs mass. And we think this is unnatural, or many people think this is unnatural, and typical beyond the standard model approaches introduce new partners of the top quark, new colored particles with a mass somewhere between say a few hundred GeV and a TeV to cancel these ultraviolet sensitive pieces. And the second important motivation for physics, new physics at the LHC, I think, is dark matter, because as you know, the Rayleigh density of dark matter in the universe can be explained in a fairly kind of natural way by weakly interacting massive particles with masses somewhere between a few hundred GeV and a TeV maybe. And so these are the 2 things that tell you some new physics has to happen at the scale of a TeV or below, a naturalness problem and maybe dark matter. And then many models try to combine these 2 things and come up with proposals and ideas that include new particles at the TeV scale to cure the natural as a hierarchy problem, and then you have a weakly interacting, massive and stable or long-lived particle that is also part of the spectrum of new particles, and then the generic new physics signature that we've been looking for at the LHC for some time now is these cascade decays that we heard about earlier today. So you produce these new heavy particles, colored particles, and then these decay step by step. They release energy in form of jets and leptons, and at the end of this decay chain you have this dark matter particle. This is a fairly generic feature of these class of models that try to explain naturals and dark matter. Supersymmetry is a prime example, but it's not the only example. Theories with universal X-ray dimensions or additional global symmetries often have this typical pattern here. And that has driven, I think, many searches at the LHC. Why we were so sure that we would find, say, supersymmetry at the first run of the LHC, or not sure, but why did we have high hopes to find supersymmetry? So people, including ourselves, did global analysis of supersymmetric models. And we fit these models to precision observables like the anomalous magnetic moment of the muon, the dark matter relic density. And what we found was that if supersymmetry should accommodate all these experimental observations, these particles, the new SUSY particles, should be relatively light. So what you see here is all the supersymmetric particles of the minimal extension, the supersymmetric extension of the standard model. And here you see the masses. You can see lots of particles with masses somewhere between 200 and 400 GeV, and here are the strongly interacting supersymmetric particles with masses somewhere below a TeV. That was the general expectation, right? If you want to get G-2 right and dark matter relic density, you'd expect in this class of model a relatively light spectrum of SUSY particles. That, as I said, was before the LHC turned on. We looked at the sensitivity of the LHC, and you could see during different analyses that indeed the LHC would be able to cover all this very easily in the first phase. So there were really great expectations. This is a picture from the gold rush. Just been to California on my sabbatical, so I was very fascinated by Californian history. These are the 49ers, which came to California in '48 to find gold, and we were like this before the LHC turned on, or me anyway. Some people say we never expected SUSY to show up, but I was very hopeful, so we were all very excited. And what happened is that we found nothing but limits, and many, many limits. You can see here a selection of the plots that we got used to. These are all limits. So you have a model, you have a parameter space, and then you exclude chunks of parameter space in many different ways. So this is what we have. And if you look a little more closely, you can see here the limits or a selection of limits that were obtained within supersymmetry by Atlas. You can see that most of these, in fact, really look for this particular signature that we just discussed. You have plenty of jets here, and most of them have missing transverse energy, except for a few. So it was really generically the type of model that people have looked for in various different ways, but generically speaking, you were looking for jets and missing transverse energy, and this was, I think, motivated by this idea of finding a theory that would solve the hierarchy problem and also describe dark matter. You can see now the limits really are near the TeV scale, so typically masses up to a TeV, even up to 1.7 TeV in some cases, have been probed. Here is a similar compilation by CMS, not on supersymmetry, but other beyond the standard model approaches, leptoquarks, large extra dimensions and things like that, generic monojet searches and so on and so forth. And you can see that in many of these cases you now probe the TeV scale. You use the TeV scale. In some cases you even push higher to higher scales, up to 10 TeV or so. And so no sign of new physics has been seen. Obviously, these are all limits that were obtained in these specific models. But you can see the general approach was to take a model, your favorite model, this particular version of supersymmetry here, the constraint CMSSM or whatever, and then you would do an analysis in this particular model. This is sensible because it's straightforward. It's the most sensitive thing you can do if you look at this particular model. But of course, you may wonder now, are we doing the right thing? Are we not overlooking something? Shouldn't we do something that is more generic and less model specific? And this is what I want to discuss in terms of searches for new physics within simplified models. So let's first briefly review how you do this very specific analysis from sort of a theorist's point of view. It's all straightforward. You've already seen that the cross-section, first of all, that you expect for new physics model is very small compared to sort of a generic LHC cross-section. So here it's a cross-section for producing B quarks, W's and Z's. And the SUSY signal cross-section at the LHC would sit somewhere around here. So there's a lot of background, and you have to find clever ways to suppress backgrounds. And so typically, as we heard earlier today in John and Cora's talk, what you have to do is you have to impose cuts, in particular cuts on things like transverse momentum or transverse missing energy. And if you look at large PT and large ET miss, you expect an enhancement of your signal compared to the background that's shown here. This is this particular distribution, which is determined by the sum of all the transverse momenta of the jets, the missing transverse momentum. You can see here the standard model expectation, the background from QCD and so on. And here you would see the expectation from a specific SUSY signal. This point has already been excluded, of course, but this is what we were expecting sort of to see in the early phase of the LHC if our optimism was justified. And so what you see in a way, what I wanted to say here is that the selection cuts that you do depend on the model and on the specific signature. So you really take a signal, you take a model, you work out what you expect in terms of signature, and then you optimize your analysis to really obtain the best sensitive limits or the best sensitivity for this model. So this is what I would call a brief and rough summary of what you do. So you have a specific model in mind. What you do is you take this model, you implement that into a Monte Carlo event generator. Say you are looking for supersymmetry, so you take your SUSY model, you implement that into a Monte Carlo event generator. Then you look at the experimental signature as a function of the parameter space of that model. That could be masses, but it could also be more generic parameters. Sometimes you use benchmark scenarios, and sometimes if the model is really simple, you just scan a 4-dimensional parameter space, for example. And then within that model, you determine the acceptance and the efficiency as a function of these parameters, and then you interpret your experimental results as a function of this small model parameter space. And that is what leads to these kind of exclusion plots that we've seen over and over in the first round of LHC searches. Here is a specific example, a specific supersymmetric model that has 4 parameters. 2 are fixed, and then 2 others are just varied here, and you can see then you get limits on the parameter space from different types of searches. So this is the kind of traditional way. And as I said, the question really is, do we search in all the right places? It's not so clear. We look at a very specific model. This is all very model specific. Do we search in all the right places? And then if we have experimental limits, can we interpret those limits in a wider class of models? So if I get this presented in an Atlas paper, can I then take my new theory, my new model, my slightly revised model, and interpret this model in terms of these searches? For example, what happens if I change this parameter here, change tangent beta to 5? Could I just take these limits and put limits on my new model, or would I have to redo things? That's not so obvious. And if we see new physics at some point, then the question is, can we really characterize what we see, not in terms of 1 specific or 2 or 3 specific models, but in terms of the properties of new physics that are really essential for this particular signature, say masses and cross-sections. So we want to rely on as little as possible assumptions on the new physics model. And that's the idea. And here's an example of what happens if you impose a specific model, or if you interpret your search in a specific model. Say you look at a signature that involves jets, so 1, 2, 3, 4 jets, and missing transverse energy. So this typically comes from a process where you have new particles that are being pair produced, and then these decay into jets and missing transverse energy. And what really determines this signature is not the details of the stuff that happens here or here, but it's really essentially the two masses that appear here, the mass of the new particle here and the mass of this dark matter particle, and then the overall cross-section times branching ratio. These are essentially the three parameters that matter. And now it would make sense, of course, then to interpret your experimental searches in terms of these three physical parameters rather than the parameters of any specific model. And if you do that, then what you get are cross-section times branching ratio limits in the parameter space of the physical masses, say the mass of this particle here and the mass of this particle here. So this is a sensible thing to do. If you don't do this, and if you look into a specific model instead, you find that sometimes within these models you have certain assumptions and restrictions on the relative size of these masses. And instead of probing this whole parameter space here, you just probe a small slice of the parameter space, because in the model these two parameters may be correlated for some reason, for some theoretical assumption that is included in the model. So you're really not exploring this parameter space fully, but only look at this small little slice that you have in this model. And so this is why people then introduce what's called simplified models. So those are really something that are, these are things that are somewhere in between theory and experiment. I think there is some sort of mediator or intermediate step between a theory and an experimental signature. And what you're supposed to do is, if you have a theory like supersymmetry that involves many complicated decays and many parameters, all these different decays here. So this is supposed to be a decay of a SUSY particle down to the dark matter particle in many different ways. So you're really supposed to condense that into simplification of this more complex scenario to what is essential for your specific experimental search. So you're supposed to remove the model details that are not relevant and to focus on the kinematics when you design your search and when you interpret your search in terms of the new physics model. So this is really the idea. And so instead of taking a full model with all these different types of decays and particles that can appear at intermediate stages and all depend on certain parameters, what you do is you interpret your search in terms of very few simple topologies, like 4 jets plus missing ET and maybe 4 jets plus leptons plus missing ET. That was the idea of a simplified model. And so what you do is you get a much simpler description, which does not depend on all these model-specific parameters, but rather on the physical parameters like the masses of the new particles and cross-sections and branching ratios. And you do not impose constraints on some of these parameters that are model-specific. So in one particular SUSY model, for example, the mass of these two particles really is not independent, but it's given by some theoretical assumption to be just 6. And if you impose that model, if you search for the specific model, as I said, you would just look along that slice here, but not explore this parameter space. So this is the idea, and what you then do once you find a signature, you extract the parameters that are essential for this particular signature. That is masses, the masses of the new particles, the cross-section, and the branching ratio. That is the idea of simplified models. So you see they are, in a way, not real theories, because this is not a complete theory. They're really driven by signatures, and they're supposed to help theorists and experimentalists to explore a wider range of parameter space in signatures and also in theoretical models. So now I want to show you some recent things we've been doing in terms of simplified models for Higgs physics. It's kind of a new research project that I started at SLAC with people there, Joanne Hewitt, Tom Rizzo, and Matt Dolan. And I'd like to explain how we can use this idea of simplified models to explore new physics in the Higgs sector. And so again, that hopefully underlines the generic idea. So to start with, I don't think anybody has shown this today. So this is what we know about the Higgs, or the new particle that we discovered. So what is shown here is what's called the signal strength. So that's the ratio of cross-section times branching ratio as measured, divided by what you expect in the standard model. So if it's a standard model particle, all these different measurements should line up near 1. So this is searching for Higgs in 2 photon decays in 4 leptons, lepton neutrinos, BB bar, and tau tau. And you can see that here in Atlas and CMS, all these measurements are kind of scattered closely around 1. So as far as we know right now, the new particle really looks like not a Higgs, but even like the standard model Higgs. So everything is consistent with what you would expect from a standard model Higgs. Now the question is, how could you explore physics beyond the standard model in Higgs physics? And the first thing that people did was to introduce what one may call a phenomenological model. So what you do is you take the Lagrangian of the standard model, which is determined by the symmetries, and you multiply each term with an arbitrary parameter. They are called kappa for some reason. You can see the interaction between the Higgs boson and the Z boson, between the Higgs and the gluon, between the Higgs and the W, and so on, is all modified by this arbitrary parameter. So that in this idea of measuring cross-section times branching ratio, the standard model expectation would be modified by products of these kappa parameters. So Higgs production in gluon fusion and decay into photons would be the standard model prediction times this kappa factor here, this kappa factor here, where is the photon? Here, and then the kappa factor for the total width. So this is very simple, but the problem is it is not connected to any theory, because there's no theory where these parameters could vary independently, because they are all tied in some way through symmetries or other assumptions. So really, this is not a theoretical model. There's no explanation of things that we could measure. It's really a parameterization of data. So it's a good first step, but it's not a good way to further explore the Higgs sector, because it cannot be that these parameters can be completely arbitrary. That cannot be. In any theory that you can imagine, there is some structure here which you can't really neglect, and so there are correlations between these different couplings, and you cannot really eventually vary them independently. But as I said, it's a nice first step to just see if there is anything in the data, but if you want to go further, this phenomenological model is not such a good idea. What's better, in principle, is to move to what is called effective field theories. So this is also well known in the standard model. Here, for example, you have a graph that determines the interaction between the Higgs boson and the gluon. So the Higgs doesn't carry color, it doesn't couple to gluons directly, but it couples through sort of a quantum fluctuation of a top quark. And if the top is much heavier than the Higgs, you can describe this complicated process by an effective interaction operator with a coefficient that you can calculate. So this is the generic idea of a field theory, an effective field theory. If you have something happening in a quantum fluctuation at a scale that is much larger than the scale at which you probe this process, so if the top mass is much larger than the Higgs mass, you can really shrink that to an effective operator. You calculate the coefficient, and then you expand in powers of this new heavy physics scale. In this case, you would expand in powers of the top quark, but you can imagine that there are other new particles in this loop, say a heavy top with a mass of a TeV, say, and then you can work out this interaction in terms of these operators, which all have coefficients that, in principle, you could calculate if you had the theory. If not, you treat them as free parameters, and you organize these operators in powers of the new energy scale, which appear in inverse powers here. So the effect of the higher dimensional operators are more and more suppressed with powers of this new physics scale. So this is nice, because what you can do now is you can really rely on the symmetries to write down all the possible operators that you can imagine that could connect, say, a Higgs boson and gluons. It's just based on symmetries, but it still gives you a certain structure, because you can see that these operators are not independent. So it's a nice way of doing it. The problem, though, is that this approach only works as long as this new physics scale, say the mass of the particle that appears, in this loop is much larger than the energy scale at which you probe this interaction. So in this case, this new physics scale has to be much larger than the energy of the LHC, the partonic energy, collision energy. If that's true, then this is perfect. It works very well, and it's a great way of going about new physics. It's model independent. It just relies on symmetries, and it's wonderful. However, at the LHC, it's not so clear that you can do that, because often if you look at new physics at scales of a TeV or so, you encounter situations where the collider energy is near or even larger than the TeV, and then this effective field theory is not even applicable. So you have this situation where either indeed the new physics is really heavy, say 10 TeV, 50 TeV, then this works fine, but the effects are really small, and probably the LHC is not the right machine to find them because there's small deviations from the standard model, or the new physics scale is closer to a TeV, in which case you may see large effects, but then this effective field theory is not the right way to describe these effects. And that's why, after people looked at effective field theories for quite a while, both in Higgs physics, also in dark matter searches, now there's been a trend to go beyond effective field theories and look at simplified models. And this is what we've been doing for Higgs physics. We've been trying to come up with new physics models that would induce effects just in the Higgs sector. And we've been trying to think about something that is really simple and really easy to construct, and this is the tricky part. So I'll explain what we've been doing, and maybe you understand some of the problems that I have with simplified models. So what we thought is, okay, let's see, we have a Higgs, and we would like to interact this Higgs boson with, say, a gluon or a photon in a way that is different from the standard model. What do we need? The simplest thing we could imagine is to add a new singlet particle that mixes with the Higgs boson and a new fermion that would couple the Higgs boson and the new singlet particle to, say, the photon and the gluon. So that looks very simple. And this is nice because now what you can do is you can look at different representations of this fermion. You can give it color, you can give it lepton number, you can put it in an SU2 doublet, you can put it in an SU2 singlet, and so on and so forth. You can play with this model and you get different predictions for the way it affects the Higgs coupling to, say, photons or gluons or Ws or Z bosons. And you can work this out. It's very straightforward. And with this kind of simplified model, really what you can do is you can explore possible theories that could give small deviations for Higgs couplings to standard model particles in a way that is consistent with what you observe. So imagine you observe a certain pattern of deviations in the Higgs sector, and then you could really look at these simplified models, at the different possibilities, and you could find the right possibility that would be consistent with data. And in this way you would kind of constrain the space of possible theories to those that are consistent with the experimental observation. So this is, I think, a nice way to use simplified models, really exploring the space of theories and also, in fact, learning how to construct these models. It's something that was very striking for me when I started with this. It was very striking to see how much I learned by just playing with these different types of models and seeing what is consistent, what is not consistent, what is constrained by other experimental observation, and what is still viable. So it's really also a way of learning about possible theories and possible signatures. However, the problems arise when you think a little more about what you mean by simple. So what is simple, really? What do you think is simple? Simple, you could say, is I want the minimal number of new particles. In this case, we just added 2 to the standard model, so that looks pretty good. And then you want the minimal number of new parameters. And that's already not so good, because if you take a complex scalar and you add that to the standard model, and you write down all the terms that are possible in the Lagrangian consistent with your symmetries, you end up with 10 additional terms, each of which has a new coefficient. So you suddenly, even if you only introduce one new particle, you get 10 additional unknown free parameters. And that's not simple, I think. So what you do, you could impose additional symmetries. So that's what people typically do in model building. You come up with something that looks complicated, and then you say, but oh, we have an additional U1 symmetry from somewhere. from the string theory, maybe. You impose that, you reduce the number of free parameters, but something else goes wrong. For example, but then if we impose the symmetry, this coupling disappears. Then we have to break the symmetry, and we have to break it in a way that does not reintroduce additional worries. So really constructing these models, you realize that it's not so easy to come up with something that's really simple and still consistent in a way that you just rely on symmetries and a minimal number of new particles. That's one thing. So it's not so clear what people mean when they talk about simplified models. The other thing is if we come up with these various simplified models, it's not obvious that we can distinguish really experimentally between these different possibilities. So I thought we can explore the space of theories by putting the fermion into different representations. But it's not really obvious that we can distinguish just from the measurement of Higgs cross-section and branching ratios between these different types of simplified models. So there may be a real problem of underdetermination in a sense, that it's easy to go from a full theory to a simplified model, but it's very hard to go from simplified models back to the full theory, because there are various possibilities that are all experimentally viable and that lead to very different full theories. So what you have to do really, I think, is you have to be able to test these models in other experiments. So what we've been looking at, for example, is ways to maybe produce these new fermions here directly and look for resonances in dijet spectra and so on and so forth. Really, if you want to use these things, you have to combine different experiments and observations to overcome this problem of underdetermination. Okay, so I'm already at the end. So here's a brief summary. I think it's clear that searches for new physics are more and more interpreted and designed in terms of model-independent approaches like simplified models, rather than the specific top-down models like the minimal supergravity model or whatever we had in mind, because no signal has been seen and we are worried that we overlook something or that we don't explore the potential of the LHC by just looking at two specific models. I think these simplified models are nice because they really allow us physicists, both the theorists and the experimentalists, to explore this kind of space of theories on the one hand, and also potential experimental signatures. And while we explore this, we actually learn a lot about signatures, I guess, but also, for me anyway, about potential theories that could explain, say, dark matter or deviations in the Higgs sector. So this is a nice tool to explore and to learn, and I think in a way they really are things that mediate between theory and data, because they're not real theories and they're not data, they are something in between. The problems that I think are not so clear, how do we actually choose the right simplified model? That's why I say it's an art in a way, because we don't have any clear prescription. It's a matter of trying things. You start with something that looks simple, you work it out, you find it's not so simple after all, you add another particle, you add another symmetry, and so on and so forth. So it's not really clear how to construct these simplified models. People come up with different ideas, and so there is a sort of ambiguity here. It's also often not clear how do these models connect to a full theory. Sometimes they are too simple, so that it's really difficult to overcome the gap between the simplified model and the full theory. In the end, we're not interested in the simplified model. The simplified model is a way to look at data and to think about searches, but it's not a way to understand how nature works. So we really want to connect these things to theory eventually. And in that context, I think you could ask, if you have a simplified model that agrees with some set of data, what does it really explain? Is it an explanation of the observation in a deeper sense, or is it more a description of what you see? It's not so clear to me in which sense these are explanations of data or just parameterization or descriptions. So these are the open questions, so I'll stop here, and thanks for your attention.